Let's get started. Welcome to the parents who've made it today. Thank you for sending us your bright people to pay our salaries and learn from us. We've spent most of the semester so far figuring out what bonds is and how quantum mechanics works and so on, but now we're trying to find out how it really happened, how people discovered how chemistry in general and organic chemistry in particular worked. And we started with Lavoisier, and now we're in the next generation, which is Berzelius in Sweden. And as we said last time, he was important for analysis. He got good atomic weights for 50 elements. We'll talk today about electrolysis and dualism. He was important for his teaching and writing. For the first half of the 19th century, he was the main man in chemistry, and his notation for composition that we talked about last time that we still use. Okay, so now we're going to talk about atomic weights and equivalents and what was involved there. We started this last time, remember, showed how Gay-Lussac had an alternative to Dalton. There was this question about even if you knew the proper ratios of elements, what you didn't know was the ratios of the atoms that were in them, because you didn't know whether an atomic weight should be doubled or halved. So they had the question about silicon chloride. Was it SiCl, SiCl2, SiCl3, SiCl4? So how could you possibly settle something like this? Dalton did it by assuming that if you had only one compound, it had to be 1-to-1. Gay-Lussac went with the volumes of the gases that were involved, which turned out ultimately to be correct, although it wasn't really widely accepted for about 60 years. But there was another neat way of doing it, depending on crystals. Mitscherlich, an Austrian, had this device on which you mount a crystal and reflect light off it through a telescope. So when you do that, you know precisely, if it comes right up the middle of the telescope, you know exactly what direction the plane of that surface of the crystal is. So what you can do then is rotate it by a certain number of degrees until some other face of the crystal reflects precisely. And then you can measure very, very accurately what the angle between those two faces is. So that was crystallography in those days before X-ray. Okay? So here's his paper on relating crystal shape to chemical proportions. They sound like not closely related phenomena, but here he's talking about arsenates and phosphates. And here are the pictures he drew. They drew beautiful pictures of crystals in those days. If that's all you can do, you do it right. So he has but he saw that the crystals were the same shape for corresponding arsenates and phosphates, this diammonium biarsenate and the diammonium biphosphate, right? So he measured the angles, and here's his table of the angles corresponding. And you can see they're very, very close to one another. Those are the differences in tenths of degrees. So these crystals are precisely the same. Now, what could he conclude from that? Anybody got an idea where you can go from here? So you know that there's an arsenate and a phosphate with the same chemical composition, right? And they give exactly the same shape. So the things that pack together must be exactly the same. So they must have the corresponding, however many arsenates there are, arsenic atoms there are in one, there must be exactly the same number of phosphorus atoms in the other. Otherwise, they could not possibly be exactly the same shape. So now you know something. There was this need for relative atomic weights. Was Dalton right? Was water HO? Or was Gay-Lussac right that it was H2O? Right? At least in this case, this thing called isomorphism, the same shape of the crystals, provided definitive atomic weight ratios for at least some of the atom pairs. So arsenic atoms must play exactly the same role in arsenates that phosphorus atoms play in phosphates. And therefore, if you have 100 grams of nitrogen, oxygen, and hydrogen that combines to give these salts with 30.64 grams of phosphorus or 78.11 grams of arsenic, it must be that arsenic atom is 2.55 times as heavy as the phosphorus atom, right? That is, it can't be half that or twice that. It has to be exactly that, because there have to be the same number to give exactly the same shape. Okay, so there was one way of determining this ratio, but it wasn't trivial. Okay? Now here's Berzelius's table of atomic and molecular weights from the year 1831. And if we zoom in on it a bit here, you can see he gave two columns for the atomic weights, one based on oxygen being 100 units, and the other based on H with a bar across it being 1. Now, the bar across atoms means that the atoms are doubled. You can have it without a bar, which is a single atom, or the bar across, that means it's a doubled atom. So he had, actually, you notice if you go down the column there, that if you assume H2 is 1, then obviously H here is a half, right? So these were the numbers he had in 1831. And we could compare them with what they would be nowadays if you scaled to oxygen as we define it now to be 15.9994. And then you see that they're off by about 1% up or down. How does that compare with what Dalton was getting? Do you remember how accurate he was? He was about 10%. So here in 25 years, they've gotten tenfold more accurate in what the atomic weights are. Okay. Now, combustion analysis was and would continue to be, from the time of Lavoisier right through the whole 19th century, the heavy carrier for organic chemistry. Okay, here's the way Berzelius did combustion analysis. So he started with a tube in which he put half a gram of organic substance that was going to be analyzed, 3 grams of sodium chlorate. Remember, that's what Gay-Lussac used to burn things with. Why that rather than air? Why did Gay-Lussac use it rather than air? Do you remember? Because a lot of things wouldn't burn in air, right? They would char. Okay, so but they used Gay-Lussac's oxidizing agent, and 50 grams of sodium chloride was ground up with this stuff, just so that the reaction wouldn't get out of hand, so it wouldn't explode. Okay, so those are put in there. Then he heated up the neck and drew it out, and plugged it into that bulb on the right. So he joined it to that bulb, which would serve for collecting water, which is a combustion product, and a calcium chloride drying tube, which would get the rest of the water that didn't condense in the bulb. Okay. Then he assembled this thing along the bottom so that the gases that came out after the water was removed would exit and be collected in this bell jar over mercury. And in that, there was a bulb that floated, which held potassium hydroxide, solid potassium hydroxide, which would absorb the CO2, thereby separating it from the oxygen that would come through. You get oxygen just by heating sodium chlorate. Okay? And then he closed the top with a piece of glove leather so the mercury that it was floating on little drops of mercury wouldn't get in, because as you know from hefting it, that would change the weight a good deal. Okay? So what he did was build a fire and move that barrier back so it would heat from one end to the other, and the gases would come out and bubble up in the bell jar, right? And fill up a good deal of the bell jar, right? And notice that the tube had been wrapped with metal to keep it from popping when it got hot in the fire, because there'd be pressure inside in order to bubble through the mercury. Okay, so then he cools it off, the gas contracts, right? The KOH absorbs CO2, so you're left with oxygen in the bell jar, and the CO2 is absorbed on the potassium hydroxide. But he then, so the mercury rises as the gas gets absorbed. But after the mercury stops rising, he waits 12 hours to make sure he's got all the CO2 absorbed, because it has to get through the glove leather, right? So it takes quite a while. It took much more than a day to do an analysis. So after it stops rising, he takes it apart, takes the glove leather off the top, weighs it, and finds out how much CO2 there was. So he's got the water and the CO2, therefore the hydrogen and the carbon. And this was a much better way of doing it than Lavoisier's, which required 3 or 4 people operating that big machine. Okay, electricity was another really important contribution from Berzelius. Okay. But it also was a contribution at the Royal Institution in London, where this is a demonstration of N2O at the Royal Institution. But the guy holding the bellows there is Humphrey Davy, who became the head of the Royal Institution, and was the head then of big science. So in 1807 and 8, he made some very important experiments. It was based on the work of Volta, who was just a little more than a decade earlier, who had invented this thing shown on his desk here, which was the voltaic pile, which was a pile of copper and zinc discs. And when you put copper and zinc together, you can get 1.1 volts out of it, okay? So this was going to be big science. So he put together 24 such pairs of things, which meant he could get 26 volts. Those were 6 inches square, right? Then he made another, there's the battery, incidentally, that Berzelius had, which is still in Stockholm. Okay? Then he put one with 100 such things, so he could get 110 volts. Then he made another one, they were only 4 inches square now, of 165 volts, right? And then he could hook them together in series. So he could get 301 volts across this thing, and then he tried doing experiments with it. So this is what he said. I acted upon aqueous solutions of potash and soda. You know what potash is? Potassium hydroxide, and soda is sodium hydroxide, saturated at common temperatures by the highest electrical power I could command, and which was produced by a combination of voltaic batteries belonging to the Royal Institution, containing 24 plates of copper and zinc 12 inches square, 100 plates 6 inches, and 154 inches square. So this is that battery I showed you. So he put 300 and whatever number of volts across this thing. Though there was a high intensity of action, the water of the solution alone was affected, and hydrogen and oxygen disengaged, with the production of much heat and violent effervescence. I can believe that. Okay, so he wasn't about to give up, he tried again. The presence of water appearing thus to prevent any decomposition, I used potash, so potassium hydroxide, in igneous fusion. So he put a flame to it and melted it. By means of a stream of oxygen gas from a gasometer applied to the flame of a spirit lamp, which was thrown onto a platinum spoon containing potash. This alkali was kept for some minutes in a strong red heat and in a state of perfect fluidity. The spoon was preserved in communication with the positive side of the battery. I don't know how he held this thing. Of the power of 106 inches, highly charged, and the connection from the negative side was made by a platina wire. By this arrangement, some brilliant phenomena were produced. The potash appeared a conductor in a high degree, and as long as the communication was preserved, a most intense light was exhibited at the negative wire, and a column of flame, which seemed to be owing to the development of combustible matter, arose from the point of contact. Right? Then he did another experiment. A small piece of pure potash, which had been exposed for a few seconds to the atmosphere so as to give a conducting power to the surface, was placed upon an insulated disc of platina, connected with the negative side of the battery of the power of 250 of 6 and 4 in a state of intense activity, and a platina wire communicating with the positive side was brought in contact with the upper surface of the alkali. Small globules having a high metallic luster and being precisely similar in visible characters to quicksilver. What's quicksilver? Live silver, right? Mercury, of course, okay? Some of which burnt with explosion and bright flame as soon as they were formed, and others remained and were merely tarnished and finally covered with a white film which formed on their surfaces. What was this? Right, he electrolyzed, here he says, potash, potassium hydroxide. What did he get? Potassium metal. So he discovered a new element. And from soda, he got sodium. From potash he got potassium. Okay, now this was a great triumph for English science, but this was a period of great rivalry, 1807 and 8. The Peninsular War was going on in Portugal, Spain, against the French, in particular against Napoleon. Now, Napoleon had studied science a certain amount as a student at the École Militaire in Paris. In fact, he had been examined by Laplace, Lavoisier's colleague in measuring heat. So he wasn't about to knuckle under to England in this. So he got his crew together, including Gay-Lussac, and said, why haven't we discovered this? And Gay-Lussac said, we don't have the battery. He says, you've got your battery. So this was the battery that Gay-Lussac constructed, according to... So it consisted of 600 1-kilogram copper plates and 600 3-kilogram zinc plates. So he had 2.6 tons of metal, and in 6 different troughs here. And then he hooked them together in series. So he's now got 650 volts. Now, Napoleon was interested in science, so he came to visit the lab one day, and there's an account of this in the biography of Humphrey Davy. With that rapidity which characterized all his motions, and before the attendants could interpose any precaution, he thrust the extreme wires of the battery under his tongue and received a shock which nearly deprived him of sensation. After recovering from its effects, he quitted the laboratory without making any remark, and was never afterwards heard to refer to the subject. Okay, so that was the end of the French competition with Humphrey Davy, but Davy himself built one with 1,000 plates, so 2,200 volts, and with this he was able to prepare a bunch of elements. In addition to sodium and potassium, boron, magnesium, calcium, and barium were all due to Sir Humphrey Davy. But that wasn't really the most important thing for chemistry. It supplied more than new elements. It supplied an idea. And the idea was the organizing principle for what was called dualism. And dualism was the idea that there were things that were positive and things that were negative, and they would be attracted to one another. And not only would they be attracted to one another, but they could trade partners. Okay? So remember we saw last time that the alchemists already had vitriolum cupri, or copper sulfate. So here we saw last time was copper sulfate. Let me see if I can get this thing going here. Here, got it. Does it have to warm? There we go. So there's copper sulfate, nice and blue. But let me get the light behind. That should be good. Okay, so we'll put some in here. So this is copper as a positive stuff, and sulfate as negative stuff. And now we'll take sodium hydroxide, and put a little bit in. So there's a precipitate. And actually it's much more complicated than people thought it was in those days. It gets quite dark blue if you put a lot in there. But now a whitish precipitate's going to form, which you don't see very well here. Maybe it doesn't know how to focus on that. See if I can get something for it to focus on. There you see the precipitate. Okay, so obviously something happened, right? And according to dualism, this is what happened, right? You mix it with caustic soda and you have A, B, and CD, positive and negative on the left, sodium hydroxide, copper sulfate, and they change partners and you get a precipitate. So you have, it's explained by electricity, and this then is what dualism was. So we've noticed that this is our family tree, you remember. And now we've looked at elemental analysis, atoms, and dualism. Notice that people are entered into this not by when they made their contribution, because they made it at many different times, but by when they were born, so you can see what the generations were. So first we had Lavoisier, then Berzelius, and now we're into a new generation of people who are going to contribute when they get to be 20, 30 years old down here. So the next thing we're going to talk about is urea and isomers, and the benzoyl radical, and the theory of substitutions and types. Okay, and our players are Jean-Baptiste André Dumas in France, and Liebig and Wöhler in Germany. And they were all born right around 1800, between 1800 and 1803. Okay, and here they are on the outside of the building. So we're going to look at Wöhler and Liebig. Now, here's Wöhler writing to Berzelius in Sweden. He's going to be the next generation, saying, having developed the greatest respect for you through studying your writings, I've always thought it would be my greatest good fortune to be able to practice this science under the direction of such a man, which has always been my fondest desire. Those who have seen such letters will recognize these as consistent up to the present day. He goes on to say, although I earlier had planned to become a physician. Okay? And at the end he says, with the greatest respect, Friedrich Wöhler from Frankfurt am Main. He was a great guy. They carried on a correspondence their whole lives. It's really entertaining. And partly because Wöhler had sort of a lamish sense of humor and was a cartoonist. So for example, in this letter to Berzelius in 1837, so this is 10 years later. He said, "To see this old friend Palmstedt again, especially here in Göttingen, was a real delight. He was just the same old guy, with the sole exception that he no longer wears the little toupee swept up over his forehead as he used to do." So Wöhler drew this cartoon in there. Okay, but what you know Wöhler for probably is urea. How many people have heard about Wöhler and urea? Okay, but the interesting thing is that the urea was not the main contribution. He also invented aluminum, incidentally, or discovered aluminum. But urea wasn't really the main, for our purposes, wasn't the main contribution from this work of Wöhler. And you'll see that there are a couple problems for next Wednesday and readings on the web that support this with original documents. So he wrote in 1828 to Berzelius, "Perhaps you still remember the experiment I carried out in that fortunate time when I was working with you, in which I found that whenever one tries to react cyanic acid with ammonia, a crystalline substance appears which is inert, behaving neither like cyanate nor like ammonia." So that's what was funny, that it didn't behave like you would expect for ammonium cyanate. So the idea was it should be a double decomposition reaction, this dualistic thing, where you change partners. So you start with ammonium chloride, silver cyanate, that was another way he did it. And you should get ammonium cyanate and silver chloride, which is a precipitate, so then you've prepared ammonium cyanate. But you can test whether ammonium cyanate is the salt ammonium cyanate. One is to see whether it has the ammonium ion in it, and that you can tell by pulling the proton off and changing it back into ammonia, which you can smell. Okay? But when he treated it with sodium hydroxide, he didn't get ammonia. Okay? Or you can test so it doesn't behave like an ammonium salt, nor did it behave like a cyanate salt. If you treat it with acid, you don't get the smell of cyanic acid. And if you treat it with lead, you don't get lead cyanate. So it appears not to be either ammonia or cyanic acid anymore. Okay? But what it did do when treated with nitric acid was to give brilliant crystal flakes. So the crystals were what allowed him to identify it. And he knew that you got the same thing when you treated urea with nitric acid, just like those from urea and nitric acid, right? So this raised the question. Berzelius wrote to Wöhler in reply to that, "It is a unique situation that the salt nature so entirely disappears. It doesn't look like dualism anymore when the acid and the ammonia combine, one that will certainly be most enlightening for future theory. So might ammonium cyanate actually be urea? Might urea be ammonium cyanate with very curious properties?" So Wöhler wrote back to Berzelius, "I recently performed a small experiment appropriate to the limited time I have available." He was doing a lot of teaching at this time, "which I quickly completed and which, thank God, did not require a single analysis." That was what was a pain in the neck to do. Okay. So this is the data from Wöhler's letter, and the same thing was published as his paper in 1828. So it turned out that Dr. Prout, a physician in London, had already analyzed urea and reported its composition in terms of nitrogen, carbon, hydrogen, and oxygen, that is its ultimate analysis. And Wöhler, without doing an experiment, knew what the analysis should be for ammonium cyanate, right? Because he had Berzelius's atomic weights. So he could calculate for a substance of that formula what the percent by weight should be, and they agreed, as you can see, very, very well. So it looked like urea and ammonium cyanate had the same analysis and therefore were the same thing. Okay? The discrepancies were less than 2%. Remember, the atomic weights are only good to about 1%. Okay, so therefore these things appear to be identical. In fact, it's interesting to compare them with the modern values, which you see here. What do you notice in the first row? When you compare the numbers in the first row, Russell? What's the same? Which is better, experiment or theory? What? No. The first is Prout's analysis, the first column. The last column is Berzelius-Wöhler theory, and the middle is what we think is correct because it's based on what we have now. What do you say? Aha! So there's a good lesson for us, right? Experiment is better than theory. But if you look more closely, there's a much more interesting story here. So the moral is don't dry lab, don't be like Lavoisier and try to make your experiments conform to theory, right? So because of that, Dr. Prout has gotten a reputation among historians of science as a paragon of accuracy and honesty, the very model for lab work, right? Okay, but let's look more carefully. You notice, for example, that he didn't make these things add up to 100%. Would you expect them to? What would happen if it had been Lavoisier doing it? What would they add it to? 100%, exactly. Here it isn't. Why not? Because he's being honest. Maybe. Okay, so notice incidentally that the theory didn't add up to 100%. Now how do you get those numbers? How would Wöhler have gotten those numbers? He'd decide how many atoms of nitrogen, hydrogen, oxygen there are in the compound. He'd see, according to the atomic weights, how much each of those would weigh. He'd add them all together, that would be the total, and then he'd divide each one by the total to get how many percent it was. Is that clear to everyone, how you do about it? So how do you do that and not get it to add to 100%? Well, I recalculated it using Berzelius's numbers, and that's what I got. Now, you'll notice a couple things here. One, here you'll notice what? That he just truncated numbers. He didn't round them off, right? So it's always going to be low, and indeed it is low, his sum. But that's not low enough, right? What else do you notice? Angela? He switched the numbers in the last row. He made an error, but the important thing is he didn't notice he made the error. He added it up and thought it was 99.8 and thought, well, what the heck, it's 99.8. It didn't, because this was early days of doing this kind of stuff. Okay, now, so we come over to Dr. Prout. Is this experimental candor? Well, you find out if you add the numbers, it's actually 99.945. He added wrong. Okay, and now, but those things really agreed, right? Now you wonder, how did old Dr. Prout do this to measure it to 1 part in 5,000, right? It turned out he measured the volume of the gas, and what he reported was 6.3 cubic inches of gas, right? So was he just lucky that it happened to be right to 4 significant figures? No, because that's not how he did the experiment. What he reported was not actually experimental. He had a theory about atomic weights. His theory was that everything was made of hydrogen, which isn't so far wrong in terms of weight, right? Because a proton and a neutron have the same weight. A proton is hydrogen. So everything is a sum of protons and neutrons. For weight, the electrons don't count for much, right? So it's not actually such a bad theory. So in his system, carbon was 6, oxygen 8, nitrogen 14. You know, that was what integer you multiply them by. Incidentally, hydrogen was called protyle from from ila prote, which means the first substance, okay? So he had this theory. So what he did was do approximate analysis, get about what the ratio is, figure out what the ratio should be in terms of small whole numbers, and then multiply them by his atomic weights. So these numbers are not really experimental numbers. They're more like Lavoisier, right? So, so what he said was it was 1, 1, 2, 1, and that gives those numbers, okay? So Prout did dry lab by making an approximate analysis and reporting results corrected by his theory, and so much for the paragon of accuracy and honesty as far as we would see it. Okay, but his theory was better than Berzelius's experiments. That's interesting. Okay, so now ammonium cyanate to urea, let's review that from the point of view of what we've been talking about. So you have ammonium. What makes it reactive? Dana? High HOMO or low LUMO? It's got a positive charge. That's one clue. Anybody got an idea? John? And what do you suppose that low LUMO is? In terms of localized orbitals, we're not going to talk about things that go over the whole molecule. There's not much to deal with here at ammonium. Yunju? Can't hear very well. Sigma star of NH. Okay, so that'll be the LUMO. How about a HOMO on the other side? There's a hint. Okay, the unshared pair on nitrogen with a negative charge. Okay, so we've got these, and we can do the make and break trick. Attack the sigma star with that. Right. So we've got back to ammonia and cyanic acid, a possible starting place for getting there. But if you have these two things, you can react them with one another. What makes ammonia reactive? NH3. The high HOMO, the unshared pair. And how about the cyanic acid? What do you see there? It looks like a functional group. Don't worry too much about how big it has to be. Just see something that looks familiar. CO double bond, pi star, right? Okay. Now, so one of these can attack the other, and we could arrange them like that and draw a curved arrow. And we could attack the CO double bond, but you could also attack the CN double bond. And in fact, these aren't so different. Because when you attack one and make an unshared pair on the other, in this case, for example, that high HOMO on the nitrogen, the N minus, can be stabilized by mixing with the pi star of the carbonyl, right? So you could actually draw it either way. So it really doesn't make any difference which way you draw it at the beginning. But what you can do is then have a further reaction of the HOMO on the bottom reacting with the sigma star again, although they probably can't line up right within a molecule. It's probably one molecule attacking another molecule to do this, okay, and get the hydrogen transfer, and that is urea. Okay, so there's how you go from ammonium cyanate to urea. It's quite an easy chain of events. You could have done it the other way too, like that, and you'd get this compound, but those molecules, the urea and this one, can lose a proton, go back on, lose, go back on, one side or the other. And ultimately, you get the one that's more stable, which is the one that has the carbon-oxygen double bond, which is a very stable molecule, a very stable grouping, as we'll learn later in terms of lore. You can actually understand it in terms of HOMO-LUMO mixing here, too. But at any rate, that's what happened. So the question arises, can ammonium cyanate exist? Or does it always change? Is there such a salt? Or does it always change to urea? And in fact, Dunitz, our old pal and your great uncle, in 1998 with Kenneth Harris, did an X-ray structure that showed that you can have ammonium cyanate. This was the first time it had ever been proved to exist. And there's what it looks like. But notice the nitrogens on the ammonium there point toward oxygens, not toward nitrogens. So it's not, so you couldn't, from this arrangement, you couldn't have done that thing the mechanism that we drew in order to get from here to there. Okay, so, but the fact of getting urea, a product of animal metabolism, from purely, as far as they were concerned, inorganic things, which is said to have done away with the idea of vitalism, was not, from my perspective, the most important contribution here. Because this is what Wöhler wrote toward the end of that paper in 1828. I refrain from all considerations which so naturally suggest themselves from this fact. That is, that ammonium cyanate and urea have the same analysis, especially in respect to the composition ratios of organic substances, and in respect to similar elemental and quantitative compositions among compounds with very different properties, as may be supposed, among others, of fulminic acid and cyanic acid. We already did those. That was a problem early on when we were drawing Lewis structures. So two different arrangements of the same atoms. And of a liquid hydrocarbon in the olefiant gas. The olefiant gas, the gas that will make an oil, is ethylene, CH2, CH2. But that's very similar to that's exactly the same ratio of atoms as you have in a long hydrocarbon if it has a double bond in it. It must be left to further investigation of many similar cases to decide what general laws can be defined therefrom. Now this is an interesting point, because when people have certain tools available, they tend to think that that's all the tools that could be available, and therefore it gives all the information that's possible, right? So if what you can do is elemental analysis, you think that once you have the ratio of the elements, you know everything about the substance. But what he shows here is that there can be different substances that have the same elemental analysis, like urea and ammonium cyanate. So the possibility of isomerism showed there was more to be known than people thought when all they could do was elemental analysis. So fulminic and cyanic acid was very important, as we'll see in just a second. Now, Berzelius wrote a paper just 2 years later in 1830 on the composition of tartaric acid. Remember, we spoke before about how pervasive tartaric acid is in the 19th century in the development of organic chemistry, and racemic acid, also called John's acid from the Vosges. On the atomic weight of lead oxide together with general marks on the substances that have the same composition but different properties. So he found that tartaric acid and this John's acid from the Vosges, also called racemic acid, had exactly the same analysis their salts did, right? And here, in fact, is a picture of it. I have the actual stuff right here. This is from a cork from a wine bottle, and on top of it here, if we're lucky, see, you can see those, and we took one of the crystals and put it on the X-ray. There's what they look like. They're beautiful little crystals, and they're calcium tartrate. So remember, you get tartaric acid grows from tartar on the walls of the wine barrels. Okay, but this is what was important. I thought it necessary. He wanted to give a name for this phenomenon, things that had the same analysis but were clearly different. I thought it necessary to choose between the words homosynthetic and isomeric. The former is built from homos, equivalent, and synthetos put together. The latter from isomeres has the same meaning, although it only properly says put together from the same pieces. The latter has the advantage with respect to brevity and euphony. So it's shorter and it's easier to say. So from now on, we're going to choose isomer to talk about this phenomenon. By isomeric substances, I understand those which possess the same chemical composition and the same atomic, by that he means molecular weight, but different properties. Okay, so that's where isomers came from. So it showed there was more to be discovered. There must be something about how these pieces are put together that's different. But how can you possibly find that out just by doing reactions and weighing things? Okay? Same chemical composition, but different properties. Okay, so there's more to chemistry than the analytical composition, which is what they were good at measuring. Now we know the importance of atomic arrangement or structure. So there are 4 C's that we'll organize things about: composition, constitution, configuration, and conformation. But you got to be patient. Those will take a little while to get there. It was several more decades. Okay, now these isomers of HCNO have been calculated to death in 2004, and we actually did a problem set and showed these earlier on, but here's what they are. There's cyanic acid, and notice this is the same anion, but you pull the proton off one end and put it on the other. It's somewhat less stable, but they interconvert easily. Okay? There's the one when you put nitrogen in the middle. It's considerably higher. That's called fulminic acid. And if you put the hydrogen on the other end of that one. Now, the bottom one is what Wöhler were working with, but the top one was being studied by the other guy, Liebig, the fulminic acid. And the name comes from fulmen, which means lightning, because like so many young lads, Liebig enjoyed things that would blow up. Right? He blew the window out of the pharmacy where he was serving as an apprentice. Right? And then he went to Gay-Lussac to work on silver fulminate, which is not great stuff to work on, as people who know from fulminates know. But anyhow, in 1824, he was in Paris working on that, and Gay-Lussac noticed a paper from Wöhler on the analysis of silver cyanide and saw that they had the same analysis. So he got them together, Gay-Lussac did. Now notice, and we're going to talk much more about the interaction of those two guys, but notice in this portrait of Liebig that there's a device down in the bottom right. Remember, people, when they got their portraits made, always put something they thought was significant there. So this is what he thought was significant, and here it is. It's not the actual one. This is made by our glass blower. Okay? And you've seen it before. For example, you come by this when you're hurrying to class, and notice right there, same thing, right? Or if any of you are student members of the American Chemical Society, that's on the logo. Because that was the most important device of the 19th century for organic chemistry. It's called the 5-bulb apparatus, the Fünf-Kugel-Apparat. Okay? And it was used by Liebig for analysis. So here's how Liebig did his analysis, and you can see the 5-bulb apparatus here. So he had a tube, much like Berzelius's, in which he put burning charcoal in there to heat it up and generate the gases, but on a much smaller scale than Berzelius did. Okay, it came through a drying agent that collected the water that was a product, and then it came into the Fünf-Kugel-Apparat, which was the CO2 collector. So in here was sodium hydroxide, right? And the way it worked was it was tilted a little bit. You notice that it's propped up here with some pieces of wood so that the bottom isn't flat. It's tilted like this, okay? So the gas comes in, and because it's tilted, it bubbles from one to the next, right? So it mixes well and absorbs. So you don't, remember Lavoisier needed a guy standing there to stir those things so that the CO2, this was self-collecting, right? And then at the end, you cool the thing off. Now, what do you notice about the bulbs here? They're different size. And you had to put it this way, not this way. Why did you have to do it this way? Because what happened at the end? You stopped the fire, and it would suck back. So this had to be big enough to hold all the liquid. This one didn't. So they were different size. You don't want to make both of them big because you want to keep it as light as possible. It was made out of very thin glass. So there's only one that still exists that Liebig had. And so it was tilted for the reason we said. And here's the original one, which is still in Gießen in Germany, where he was a professor then. Right? But this was a great advance because with this, a single student could do 3 analyses in a day, rather than Lavoisier's big machine that required 4 people working forever, or Berzelius, which required waiting overnight for the CO2 to be absorbed all and so on. So this was the most important thing, and everybody, all the students who wanted to be organic chemists went to learn how to do this in Gießen. So Liebig is almost everyone's great whatever grandfather in chemistry, because all the people who went out to teach studied how to do this with him in Gießen. So here's a portrait, a little bit later portrait of Liebig after he had gone to Munich to be a big wheel. But again, he chose in his portrait to have a picture of the Fünf-Kugel-Apparat. But if you look at it carefully, you see something very interesting. You see what it is? As far as I know, no one ever noticed this before. It's hooked up backwards. How could he possibly have hooked it up backwards? He must have told hundreds of students over the years, look, when you put it together, you put it this way, not this way. It's like which tube of the condenser you connect to the water, right? It's exactly the same kind of thing, right? So I just think that's amazing that he didn't notice that. But anyhow, there we got it backwards. Okay, this was his teaching laboratory, which still exists in Gießen. It's a museum. It's interesting to go there. And there's on the wall, there's this thing, and it shows all of his students and grand students and great-grand students who became distinguished professors. And the ones in red are ones who got the Nobel Prize, the ones with red on them. And you could extend it now. This stops in the middle of the 20th century. Practically everyone's descended from Liebig, including you. Okay. This is his lab, and here, this is here's the Ortigosa from Mexico, and he was supposed to be so good at analysis that he could do better than Liebig did, right? So he's the one that got to hold the five bulb apparatus, and what do you notice about it? He's holding it upside down. The potassium hydroxide would run out, right? And this guy is A.W. Hoffman, who there's this thing of him. It's a master and shining teacher of chemistry, a triumphant discoverer of aniline and aniline dyes. And he also was the guy that was really good at languages and devised a lot of the names we use nowadays. So we'll talk about that later. And here in the background, looking through a window into the lab, it looks to me, I'm not sure that that's what it is, but it looks like a bust. Does it look like a bust to you? And if it's a bust, it's probably this bust of Liebig. So it's fun to go there. Okay, so in 1832, Liebig and Wöhler collaborated to develop the radical theory. And we'll just give an introduction to that and not go all the way through it. So Liebig and Wöhler, remember, had been introduced by Gay-Lussac, so they were of the same age and doing the similar kinds of things. So they first met in Frankfurt in 1825. And 5 years later, when they were writing, they first used the familiar, you know, like tu in French or du in Germany. If you're really great friends with someone or within the family, you use that. So they became great pals. And in 1832, Wöhler said, I long to do some more significant work. Shouldn't we try to shed some light on the confusion about the oil of bitter almonds? But where to get material, right? So, you know, Baker, J.T. Baker didn't exist then, but if they were now, they could just order up a bottle of it. So, see, can you smell this?
Yeah.
Do you recognize the odor? Here, we'll pass it around carefully, don't drop it. It's not that bad, but you don't want to drop it. And see if you recognize the odor. Like almonds, the oil of bitter almonds. Good. Okay? Okay, so in June of 1832, just the next month, Liebig wrote to his pal Wöhler and said, my poor dear Wöhler, how empty is every comfort against such a loss, because Wöhler's young wife had just died. When I think how content, happy you were during your move, what attachment and love you had for one another, the good wife so young and full of life, so irreplaceable for her parents and for you. Come to us, dear Wöhler. Although we may not be able to give you comfort, we will perhaps be able to help you bear your grief. Staying in Kassel at this time would only be detrimental to your health. We need to be busy with something. I have just been able to get some amygdalin from Paris, and I'm ordering 25 pounds of bitter almonds. You must not travel. You must busy yourself, but not in Kassel. I haven't had the courage to tell my wife yet. Come to us. I expect you at the end of this week. No, what he didn't want to tell her about was the death of Wöhler's wife, obviously. Okay. So then in July, Wöhler says it came. The oil of bitter almonds has come with the books from Paris. I've kept half of it and I'm herewith sending you the rest. I've already started all kinds of experiments with it without being able to obtain any precise results. It seems to be a hard nut. This is an example of Wöhler's lame sense of humor. He did this all the time. I'm coming soon to you and will be able to report. So they worked together for 2 weeks on this and developed the most important theory on basis of these experiments. Wöhler returned. He said, here I am again in my gloomy lonesomeness, not knowing how to thank you for all the love with which you took me in and kept me for so long. How happy I was to work with you from moment to moment. Herewith, I'm sending the paper on oil of bitter almonds. So next time we'll talk about what they did with their oil of bitter almonds.